Hi, my name is David Van Vranken. I'm here at UC Irvine in the Physical Sciences Lecture Hall, and I came here to teach organic chemistry to 448 amazing students. But the coronavirus has changed all of that. Our lecture halls are empty, our labs are empty, our buildings are empty. Our campus is empty. We've gone remote on the UCI campus, and we're finding ways to make it work, to deliver instruction any way that we can. Your job during this critical period is to stay healthy and stay engaged with the material and be interactive with the faculty, with the TAs, and with the other students. I look forward to working with you this quarter.
All right, let's go ahead and get started with the content for Chemistry 51C. We're starting with Chapter 18 called Electrophilic Aromatic Substitution. And I want to try to remind you of what you already know. Throughout this first two quarters, what you've learned is substitution of electronegative leaving groups. You've been trained to look for and identify bonds to halogens like chloride, bromide, or iodide, or bonds to leaving groups like tosylate. You've been trained to think about this process where a nucleophile can either attack the carbon atom and make a bond, or have the leaving group leave first. But ultimately, you've been taught to think about this idea of substituting electronegative leaving groups. That's the way to form bonds like this bond that I'm darkening in organic chemistry. But you have to get over that. Let me just elaborate on this by saying that while you learned that you do nucleophilic substitution of electronegative leaving groups, bonds to oxygen, bond to halogen, you never, ever do nucleophilic substitution to bonds that are directly attached. This is supposed to be a double bond here, directly attached to sp2 hybridized carbon atoms, like carbon-carbon double bonds, or even more especially onto benzene rings. So you would never do SN2 substitution, even with the best leaving group here with an iodide. You would never do an SN2 substitution on these types of substrates. So I'll just write never SN2. So we never do that. So this is what you should have picked up over Chemistry 51A and 51B. And now we're going to change all of that. In a way, it's a shame that we spent so much effort trying to teach you to learn how to substitute electronegative leaving groups through SN2 reactions or even SN1 reactions, because now, and let me just say, or SN2 or SN1 here, you don't substitute those types of We're going to teach you different ways to make bonds to sp2 hybridized carbon atoms. So starting in Chapter 18, let's just forget about SN2. We're going to teach you about a completely different type of substitution where there's no electronegative leaving groups. So in this chapter, we're going to focus on the substitution of hydrogen atoms that are attached to benzene rings. And the biggest challenge for you that's different from Chemistry 51A and 51B is we don't usually draw the atoms that get substituted. So let's go ahead and take a look at this process. So here's a substitution reaction. I'm using E as a symbol for some sort of a powerful electrophile. And I'm not going to tell you what that electrophile is just yet. You have to wait just a minute for me to elaborate on that. But here a substitution has occurred. And what makes it tricky is the thing that got substituted is the atom that we don't draw. It's the atom that we assume that you know is there. And it's an H atom. But we typically don't draw H atoms. And somewhere along the line, you should have become so good at identifying how many H's are attached to every carbon, you should know that there was one H atom there. So if I ask you what happened here, if all of you say you formed a bond between carbon and electrophile, you're missing the point that you broke the bond between the carbon and the H. That's just as important as forming the bond between the carbon and the symbolic electrophile. So that's what we're going to do this chapter 18, is we're going to learn about this completely different type of substitution reaction, where we're not substituting electronegative leaving groups, we're substituting hydrogen atoms, more specifically protons on benzene rings. Okay, what I've got arranged for you here is a list of 5 electrophilic aromatic substitution reactions. That's what this chapter is about. So we're taking electrophilic reagents and we are substituting H atoms on benzene rings. And I've done you the courtesy of drawing those H atoms here, but as we go throughout the chapter, I'm going to stop drawing those H's every time. I expect you to know that there's 6 H's on every one of these benzene rings. Now, this chapter is really about 5 reaction recipes. We're going to teach you 5 recipes for substituting H with halogen, H with a nitrogen atom, H with a carbonyl group, H with a sulfonic acid, or H with an alkyl group. 5 recipes. That's what this whole chapter is about. And it's going to seem like an insurmountable amount of work to you because the challenge here is all about not really memorizing these recipes, but about all the exceptions. But let's go ahead and start off with those recipes so that we can see what's going on in the reaction. Okay, so here's our recipes. The first recipe for forming a bond between a benzene ring and a bromine for substituting an H atom is going to be the addition of the halogen. So this is a reaction that also works with chlorine. So I'll just write or Cl2. But this isn't enough. You should have learned sometime way back in a previous chapter, like chapter 10 on addition to alkenes, that benzene rings don't react like alkenes. They're unreactive. You can't just take Br2 and add it to a simple benzene ring and get any sort of a bond-forming reaction to occur. You need a super secret reagent here. And that reagent is iron tribromide, or more correctly, ferric bromide. So if you're doing Cl2 addition, you usually use FeCl3. This is a secret catalyst. Without this catalytic FeBr3, there's no way that this reaction will work. And you simply have to memorize that additional reagent. Okay, that's your first recipe. And later we'll tell you some really important reactions that you can do with the bromine. You can't do SN2 on this, but we'll teach you how to convert that into a super powerful nucleophile. Okay, what about carbon-nitrogen bonds? When you look at drugs, a large amount of the pharmaceuticals that are sold in the United States and around the world have bonds between benzene rings and nitrogen atoms. And so it's useful to know how to put those carbon-nitrogen bonds on benzene rings. So the secret recipe that we use there is to use nitric acid, HNO3. Nitric acid is a super dangerous acid. We have concentrated nitric acid in our laboratory, but it's mainly dangerous not just because it's a strong acid, but also because it's an oxidizing acid. But it's not the strongest acid that we have in the lab, and it is not strong enough to nitrate a benzene ring. If you want this reaction to work, you have to remember to add an acid catalyst that is more powerful, more acidic than nitric acid. And the acid that's more powerful and more acidic than nitric acid is sulfuric acid. So you have to memorize this 2-part recipe for substitution of H atoms with nitro groups. And if I draw the structure of that nitro group, maybe you're not used to drawing out nitro groups. We'll get into this in more detail shortly. Here's the Lewis representation for that nitro group. There's more than one resonance structure possible. Okay, what about forming carbon-carbon bonds to benzene rings? Here's the best reaction for forming a carbon-carbon bond to a benzene ring. It involves substitution of a functional group called an acid chloride. And R can be alkyl, R can't be a heteroatom, but could be methyl, ethyl, isopropyl, another benzene ring. So when you have this type of functional group called an acyl chloride or an acid chloride, that can be used to form bonds between benzene rings and carbonyl groups. But again, we need a special secret acid catalyst as part of this recipe. And you simply have to memorize this. And that acid catalyst, it's a Lewis acid, not a protic acid, is aluminum trichloride. That's a super powerful Lewis acid that's going to grab onto that chlorine and help yank it away at some point in the mechanism. And we'll talk about the mechanisms for all these substitution reactions. Okay, next is the addition of a sulfonic acid group. I think we've already learned about tosylate leaving groups. The way that you make toluene sulfonic acid to make tosylate leaving groups is through this sulfonation reaction. And the secret recipe here is to use sulfur trioxide. So if you burn coal that has high sulfur content, the sulfur ends up getting oxidized and burning. And when that comes into contact with water, it creates sulfuric acid. So this is a powerful electrophile, but it's not powerful enough. Again, we need a super powerful acid catalyst, and the acid catalyst that we use is sulfuric acid. In fact, you can buy bottles of sulfuric acid that have sulfur trioxide saturating them, so it's maybe in a way you can get a pre-made mixture of that. But sulfur trioxide helps substitute the H carbon bond with a sulfur carbon bond. Okay, our last recipe is a little bit redundant. I showed you in this third recipe how to make a bond between a benzene ring and a carbon atom, but here I'm telling you how to put an alkyl group directly attached on the carbon atom. T-butyl, isopropyl, or groups like that. And the recipe looks a little bit similar to this acid chloride. We have alkyl chlorides or alkyl bromides or even alkyl iodides can be used to do this. And we use seemingly the same recipe that we did for the acyl chloride over in this third recipe. But the problem is with this reaction is that there's a lot of exceptions to this. And the most important exception that makes it not used very often is that you have to use the benzene in excess. You have to use this as the solvent for the reaction in order to get a little bit of the product. And so you're really throwing away most of the benzene that you put into the reaction. It doesn't end up reacting. So that's absolutely required. Oftentimes I indicate excess in organic chemistry by writing excess. You have to remember to do that if you want to convince me that you have an efficient process. Okay, this is what chapter 18 is about. It's about these 5 reactions. And you need to get out of here and you need to go memorize these reaction recipes so that you have instant recall. That's what this chapter is about. Now let me be straight with you. These are not all equally useful. So it turns out that the first 3 reactions on this list are going to be very useful. I'll just write most useful. And these are money reactions for making bonds to carbon, nitrogen, or to bromine, iodide, or not iodide, but to chlorine. So again, this would be Cl2 plus FeCl3 over here. The ones on the bottom, it's just not that common to make carbon-sulfur bonds attached to benzene rings. The reaction works, it's fine. It's just not that common. There's a few drugs that have on there like Viagra or sildenafil, some others, but because it's not a very common functional group, I would say that this is a less useful reaction. You're going to see less throughout the quarter. And then this last version of forming a carbon bond to a benzene ring is less useful and has more exceptions than this example up above where you use an acyl chloride. Usually, if you want to have some alkyl group or isopropyl group, you can put that on there through a multi-step sequence starting with this reaction and it'll turn out to be more efficient. So really, these top 3 reactions are the ones that you're going to find yourself using most throughout the rest of the quarter. But you need to learn all of these recipes for this chapter. And you need to get out of here and go practice those recipes. And there's plenty of problems in the textbook and in Sapling to help you learn those. And talk about the mechanism for these processes. They all kind of have a very similar mechanism. So let's go ahead and say what's going on here. Okay, they all involve a 2-step mechanism. And I'm going to be generic about this mechanism. I'm going to symbolize some sort of a powerful electrophile that we're generating in this reaction mixture. All those recipes are designed to generate super powerful electrophiles, more powerful than any electrophile that you've seen in 51A or 51B. And we need those powerful electrophiles because the double bonds in benzene rings are not like regular double bonds. They're not very reactive. And so we have to have super powerful electrophiles. Look at this, I'm drawing the H for you because I think you're going to forget that it's there if I don't draw it at this point. So let me go ahead and symbolize the super powerful electrophiles that we're generating with those reaction recipes by writing E+. And whether you're forming a carbon-sulfur bond or a carbon-nitrogen bond, the only thing that we're changing is E+ in these reactions. The first step is the slowest step of the mechanism. If a reaction takes 2 days, it takes 2 days because you're just waiting for that double bond of the benzene ring to attack your E+ that are floating around in the reaction. So step one, the slow step, is to get these super stable pi bonds in the benzene ring to attack an electrophile. So when we do this, when we take electrons away from one of these carbons over here, I'm going to leave a carbocation over here, we are going to lose aromaticity. And we're going to generate a very special carbocation called an arenium ion. It's got its own name. And so according to my arrow pushing, I'm going to leave, since I'm taking the electrons away from this top carbon, I'm going to leave a carbocation there. Now, notice how I drew that H atom here. The reason I draw that H atom here is because I'm going to need it in this step. And if I don't draw it here, you'll find that you're going to forget what to do at this step if you haven't drawn that H there. That's why it's so critical to draw the H at this position, is you need that for this next step. In all of these reactions, there is some sort of a conjugate acid that can pull a proton off. It can be a solvent molecule, it can be an ether molecule, it could be an oxygen from the glassware, and we don't care what the identity of that conjugate base is that's left over from our acidic conditions. So I'm going to symbolize that with the letter A. It could be a sulfonate anion, could be a FeBr4 minus, we don't care. It's not worth your time worrying about that. The important point is that this angry arenium ion, let me go ahead and write that out. Arenium ion, so we can get this language down. The point is that that anything can pull this proton off. It really wants to be an aromatic system again, and the only way to regain aromaticity is to pull off this proton and give the electrons back to this carbocation, this carbenium ion is the technical term for a carbon that only has 3 bonds and a positive charge. So you have to pull this proton off to regenerate aromaticity, and that's easy. Wow. We're not worried about what the A minus is because anything can do that, but we have to symbolize it with something. So when we do that, we regenerate aromaticity, and we now have replaced an H atom on a benzene ring with some sort of a powerful electrophile. All 5 of those reaction recipes that we showed you go through that reaction mechanism. So the reaction mechanism here. Okay, you have to get used to drawing resonance structures. Let's go ahead and start off by going into a little more detail on this arenium ion. So let me go ahead and redraw that arenium ion here so we can think about the fact that there's another alternative reaction that could have occurred but never occurs. So here's one possible resonance structure for that arenium ion, and something that you never see happen, right? If you have A minus floating around, it always pulls off the proton. What you never see happening, and I hate to even draw this, is you never see that A minus. I'll just write no. You never see that A minus attack that carbocation. Instead, it pulls off the proton, as I showed you up above here, and if you attack here, you've lost aromaticity and you'll never get it back. So the favorable reaction pathway is to deprotonate and regenerate aromaticity. There's 2 other key resonance structures we can draw for this simple substituted arenium ion where we've added the E. Let's go ahead and practice drawing those. Remember, with a resonance arrow, it's a double-headed arrow, not an equilibrium arrow, but an arrow with 2 heads on one line. The other resonance structures that we can draw, we can shift this double bond over here and leave the positive charge over at the 7 o'clock position on that ring. So let's go ahead and practice with that. Here we go. You know, since I didn't have one, I don't like to have more than one set of arrow pushing here. Since this isn't a real arrow, I feel free to draw a curved arrow to represent this process. Never have 2 different types of processes depicted with curved arrows, only one, but one of those is a dashed line, which indicates it's not really happening. And so this next arenium ion resonance structure we have would look like this, where we now have the positive charge over here at this lower left position. And there's one more resonance structure that we can draw. And we use, again, we use a resonance arrow to depict that. And that is if we shift this double bond over and attack, in a sense, we attack that carbenium ion. And when we draw that last arenium ion resonance structure, it has a positive charge or a carbocation on the other side of this atom that got substituted. Now, all of these resonance structures are pretty similar. Not any of them is more stable. These are just three different depictions of one single arenium ion. They're just different depictions. They're not different compounds. There's no rate or speed at which all of this occurs. They're just all different ways to depict the same arenium ion. So again, when you get to this mechanism, because you've spent so much time doing SN1 reactions, every fiber of your being is going to make you want to attack that carbocation. But don't do it. Don't attack that arenium ion. You deprotonate. That's what leads to the substitution product. And so fight that temptation. Right, that's what we're going to finish up with here in lecture 1. When we come back on Wednesday, we're going to be talking about the detailed mechanisms as we go through each of those 5 different recipes for electrophilic aromatic substitution. So, right, I look forward to seeing you on Wednesday and in discussion section this week and at office hours.